For our finishing part of section 2.6, we are going to look at asymptotes, the three different types in this case. So we'll run through a little overview of each one, and then in the next video, we'll have some examples. So first off, we'll start with a familiar old type here, the vertical asymptote. So the type of line that we see on a graph, a dashed line here representing the asymptote, is going to be a vertical line. We've seen these before, definitely. Vertical lines, so these are of the equation type x equals some value. So we'll just say x equals a to keep it generic. Okay, so if you're asked to find the equations of an asymptote or to find all the asymptotes of a certain function, for these vertical asymptotes, you would want to write their result as a vertical line. Okay, next question. Can a function cross or touch this type of asymptote? What do you think? If you said no, you are right. No, we cannot touch a vertical asymptote with our function, and your function cannot cross over a vertical asymptote. And this is because the function is undefined where there is a vertical asymptote. So there cannot be a function value on that vertical line. Okay. Function is undefined in general. So to find these vertical asymptotes, little refresher, you've learned this process back in algebra. To find these, you're going to set your denominator equal to 0, because we'll be looking at these in terms of rational functions, generally speaking. Set denominator equal to 0. And then factors in that denominator that can't be canceled out. Okay, so factors that can't be canceled out will create vertical asymptotes. I'll abbreviate that as VAs. Okay. Now, remember this idea of not being able to be canceled out. That is because this is a different type of discontinuity than factors that can be canceled out of the denominator. Remember, those factors that you can cancel out, those are removable discontinuities, and those will just create a hole in the graph. So for the vertical asymptotes, we're looking at things that you can't cancel. All right, next type, horizontal asymptotes. And the type of line you're going to look at here is a horizontal line. Surprise. Okay, so horizontal lines will have equations of the type y equals something. All the y values are the same all the way across. We'll generically say y equals b. Would be how you write this type. Now, can a function cross or touch this type of asymptote? What do we think? If you think yes, you've got it. All right, so yes, a function can actually touch and or cross over a horizontal asymptote. The function is still defined for these type of asymptotes here. Function is still defined. Okay, these are not an undefined type of situation. Okay, how to find this type of asymptote? Well, let's remember our definition way back from the start of section 2.6. Scroll up, it looks blank. Here we go. All right, this guy that we looked at way back in the very first video. The line y equals b is a horizontal asymptote of f of x if either the limit as x approaches infinity of f of x equals b, or the limit as x approaches negative infinity of f of x equals b. So these were the end behavior type of asymptote here. When the function levels off to some constant value. You can see in our little sample picture here, we have a function that crosses over this horizontal asymptote, and then as x approaches positive or negative infinity, it tapers off and approaches this horizontal line here. Okay, so those are horizontal asymptotes. And that's exactly how we're going to find horizontal asymptotes, is by taking limits as x approaches positive or negative infinity. So look at the limit as x approaches infinity of f of x, and or the limit as x approaches negative infinity of f of x. Okay, if the limit is constant, and that is key here, if the limit is constant, some value, we'll say b to be consistent here. So if the limit approaches a constant b, then y equals b is a horizontal asymptote. HA for horizontal asymptote. Okay, if you take a limit like this and it is not constant, for example, like we saw in this example here in number 8, our limit as x approached infinity turned out to be infinite. That does not create a horizontal asymptote. Okay. So yeah, these infinite limits, nope. But here, back in example 5, that was also a limit approaching infinity. Okay, x approaches infinity, and we did end up with a constant value of 1/2 for our answer. So y equals 1/2 would be a horizontal asymptote of this function that we were looking at back here. Okay. So those are horizontal asymptotes. And then the third type we'll look at are slant asymptotes. And this type of line is one that is not perfectly vertical or perfectly horizontal. So we'll just say that this is a slanted line. Matches the name of the asymptote type. Okay, so slanted lines, we'll just say those generically are like y equals mx plus b. Okay, some slope that is not undefined slope, that would be a vertical line, or a slope of 0, that would be a horizontal line. So m is defined and m cannot equal 0 here because that would be a horizontal line. Okay, so it'd be lines of this type. Now, can a function cross or touch this type of asymptote? Yes, also on these. Because these are not looking at places where the denominator equals 0 for the function. The function is still going to be defined for this type as well. Function is still defined. Okay. Now, how to find this type? This is, just to draw you a quick example of a slant asymptote, it would be some line y equals mx plus b. I'll just draw in this very generic dashed line here. And your function would approach that line as x approaches positive or negative infinity. So your function might do something like this. Okay. And then maybe over here it does something like this. That could be on the other side of the asymptote. All right. But notice how, as we are approaching that slanted line, the end behavior of this function as x approaches positive or negative infinity is going to not approach a constant. It's going to keep growing either in the positive or negative direction. So this type of function would have an infinite limit as x approaches positive or negative infinity. So that is worth noting just off the bat here, because you cannot have a horizontal asymptote and a slant asymptote at the same time because of exactly that reason. With the horizontal asymptotes, those limits as x approaches infinity or negative infinity have to be constant. And for the slant asymptotes, those limits literally cannot be constant. They have to grow to positive or negative infinity. So that is a good note to have on these that'll kind of help you in finding all of the asymptotes of a function. These two types will not occur together. So you might have one or the other, but you can't have both. Oops, I don't want to write over our word slant there. Okay, there we go. So these types will not occur together. They don't play nice. Okay, so how do we find a slant asymptote? Well, if we're looking at a rational function, as we often will be, okay, for these asymptote problems, in rational functions, a slant asymptote occurs when the numerator, so the polynomial in the numerator, is exactly 1 degree higher than the denominator. Okay, so exactly 1 degree, no more, no less. So that might look like a rational function where the numerator is degree x squared and the denominator is degree x to the first. Okay, so second degree over first degree, or you could have third degree over second degree, x cubed over x squared type, but exactly 1 degree higher in the numerator. And that is part of how we are going to be finding these. So to find a slant asymptote, we are going to use polynomial long division. Okay, use polynomial long division to divide, divide the numerator by the denominator. Okay, so we'll have examples in the next video. This is probably something you saw, I want to say most people would have seen this in college algebra probably, or pre-calculus, depending when and where you took it, learning this polynomial long division. And then when you do that polynomial long division, the quotient, okay, so the quotient is the result that you get from division. It's not the remainder portion, by the way. We'll make sure to differentiate between those two, okay? So the quotient provides the equation of the slant asymptote. Okay, and we will look at an example of that, but this is why you have to work with numerators that are exactly 1 degree higher than the denominator, because when you do that, just to make a very, very quick example here, like if you have x squared over x, okay, doing the division of those two functions would provide you with something that is x to the first degree. So this is making a linear function when you divide those polynomials. And we want the result to be linear because we want to have a slanted line equation for this asymptote. So yeah, that's probably a little overly simplified example, but that's the idea of why numerator has to be 1 degree higher. Okay, so yeah, in the next video, we'll do some examples of these.